The arrow of time is one of physics' greatest mysteries. The laws of nature themselves don't care about time's direction, yet time, as we experience it, only moves forward. Consider a glass shattering on the floor. The fragments scatter outward, but they never spontaneously reassemble. At the microscopic level, however, the universe doesn't favor forward over backward. The laws governing particles and forces are time-reversible. An electron behaves the same, whether moving toward the future or retreating into the past. And yet, in our reality, time flows in one direction, never in reverse. Why? This question has puzzled scientists for centuries. In the 19th century, physicist Rudolf Clausius offered a profound clue with the concept of entropy, a measure of disorder. A cold glass of water has low entropy. Pour in hot water, and the heat disperses evenly, raising entropy. Clausius discovered that in any isolated system, entropy always increases. This became the second law of thermodynamics, one of science's most unbreakable rules. Entropy, Clausius realized, defines the arrow of time. Picture a cup of coffee with cream poured in. At first, intricate white swirls dance through the black liquid, but eventually, they blend into a uniform brown. The system moves from order to disorder, low entropy to high entropy, irreversibly. But this raises a deeper, unsettling question. If entropy is always increasing, it must have been extraordinarily low at the universe's beginning. Why was the cosmos, in its earliest moments after the Big Bang, so improbably ordered? Why didn't it start in chaos? Some scientists propose that as the universe expands, it continually creates new space, new opportunities for entropy to rise, like ink spreading endlessly on a canvas. Yet this only explains what happened after the Big Bang, not why the universe began in such a special state. Others, like physicist Julian Barber, suggest something even more radical. Perhaps time doesn't exist at all. Barber imagines the universe as a timeless landscape, a collection of frozen moments, like frames of an infinite film reel. We perceive these frames in sequence, giving the illusion of flow, but in reality, past, present, and future might all coexist, fixed and eternal. Another idea comes from the multiverse hypothesis. Maybe our universe is just one bubble in an infinite cosmic foam. Most universes might begin with high entropy, where time doesn't flow. Ours could be a rare, statistical fluke, a fleeting pocket of order in an ocean of chaos. None of these explanations fully solve the puzzle. They are glimpses, not answers. What we do know is that entropy marches on. Stars burn out. Galaxies collide. Eventually, entropy will reach its maximum. The universe will exhaust all possible transformations. Stars will fade. Black holes will evaporate. And everything will settle into a silent, motionless equilibrium, a state known as heat death. Time itself will effectively cease, not because it's broken, but because there will be no change to mark its passage. That day lies billions of years ahead. For now, the glass stays shattered. The cream continues to swirl into coffee, and tomorrow still waits just beyond reach. Time carries us forward, a cosmic river flowing from the improbable order of the past toward the chaotic unknown of the future. The arrow of time remains one of the universe's deepest enigmas, hidden somewhere in entropy, timelessness, or the vast probabilities of the multiverse. Across the vast expanse of the cosmos, amidst the glittering tapestry of stars and galaxies, lies an unseen presence, an invisible force that shapes everything we know. It doesn't shine, it doesn't reflect light, and it barely interacts with the world in any familiar way. Yet without it, galaxies would tear themselves apart, stars would drift into the void, and the universe as we know it would collapse into chaos. This hidden influence is dark matter. But even stranger is something more elusive still, a force not that holds the cosmos together, but one that pushes it apart, stretching the very fabric of space itself. We call this dark energy. Together, these two mysteries account for over 95% of the universe. Everything we can see, stars, planets, gas clouds, every atom and photon, makes up less than 5%. The rest is a darkness unlike any we know, not the comforting shadow of night, but a profound enigma woven into the structure of reality itself. The story of dark matter begins nearly a century ago. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a massive congregation of galaxies bound by gravity. Using Newton's laws, he calculated how fast those galaxies should be moving based on their visible mass. The numbers didn't match. The galaxies were moving far too quickly. They should have flown apart into the emptiness of space. Something unseen was holding them together. Zwicky called it dunkle materie, dark matter. Few believed him at first, but decades later, Vera Rubin uncovered striking evidence. Studying the rotation of spiral galaxies, she found that stars on the outskirts orbited just as fast as those near the center, something impossible without a vast, invisible halo of mass surrounding each galaxy. This was dark matter's gravitational fingerprint. And yet, we still don't know what dark matter is. It emits no light, absorbs none, and barely interacts with ordinary matter. Physicists suspect it could be made of exotic particles, WIMPs, weakly interacting massive particles, or axions, entities so elusive that they have so far evaded all detection. Experiments in deep underground labs and high-energy particle colliders continue to search, but for now, dark matter remains a ghost. Then came an even deeper mystery, dark energy. In the late 1990s, two teams studying distant Type I supernovae expected to find that the universe's expansion was slowing under gravity's pull. Instead, they discovered the opposite. The expansion is accelerating. Some unknown force is driving galaxies apart faster and faster. What is it? One possibility is vacuum energy, the latent energy of empty space itself. Quantum mechanics tells us that even a vacuum teems with fleeting particles that pop in and out of existence. Over cosmic scales, their combined energy could push the universe outward. Another idea is Einstein's cosmological constant, a term he once introduced, abandoned, and which now seems to describe this repulsive force. Yet when physicists calculate its value using quantum theory, the result is absurdly wrong. Off by a factor of 10 superscript 1 superscript 2, the most infamous mismatch in physics, known as the vacuum catastrophe. Some propose that dark energy isn't constant at all, but a dynamic, evolving field called quintessence, changing over time and subtly shaping the universe's fate. But for now, these remain theories, unproven, tantalizing whispers in the dark. Together, dark matter and dark energy paint a portrait of a universe that is both majestic and profoundly alien. They remind us of how little we truly know, that most of reality exists beyond our senses, in realms we can infer but not yet grasp. And yet, we see their effects. The clustering of galaxies betrays dark matter's presence. The redshift of distant light reveals dark energy's cosmic push. These invisible forces sculpt the cosmos, dictate its evolution, and set the stage for everything we see. The search continues. In silent underground chambers, detectors wait for the faintest interaction of a dark matter particle. Astronomers scan the depths of space, searching for clues to dark energy in the glow of distant stars. Perhaps the answers lie hidden in gravitational waves, in the hum of the quantum vacuum, or in discoveries we cannot yet imagine. But maybe the universe will keep its secrets a while longer. For now, we live in a cosmos dominated by shadows, forces we cannot see but cannot ignore. And in those shadows, hidden in the silent dance of galaxies and the infinite stretch of the void, lies the key not just to understanding the universe, but to understanding our place within it. Somewhere, in the flicker of starlight and the whisper of distant quasars, the answers wait, patient, eternal, and waiting for us to find them. Imagine for a moment that everything you know, the stars, galaxies, planets, even yourself, is not quite what it seems. What if the universe, in all its vast beauty and complexity, isn't truly a three-dimensional expanse, but something far stranger, a two-dimensional surface from which our reality is projected, like an image cast by light through a film onto a screen? This is the essence of the holographic principle, one of the most mind-bending ideas in modern theoretical physics. This concept lies at the crossroads of black holes, string theory, and the nature of space and time itself. And it all began with an unsettling paradox involving information and black holes. In 1974, Stephen Hawking made a groundbreaking discovery. Black holes emit faint radiation, now called Hawking radiation, causing them to lose mass and eventually evaporate. But this presented a dilemma. If a black hole disappears completely, what happens to the information about everything that fell into it? According to the laws of physics, information cannot be destroyed. Burn a book, and although its pages turn to ash, the data they contain still exists in principle, scattered in the smoke and heat. But if black holes vanish entirely, where does that information go? This puzzle, known as the black hole information paradox, led Nobel laureate Gerard T. Hooft to propose something radical. Perhaps information doesn't vanish inside the black hole, but is instead encoded on its event horizon, the two-dimensional boundary surrounding it. Imagine a 3D object falling into a black hole, its essence preserved not inside the singularity but on the surface, like a shadow projected on a wall. Then physicist Leonard Susskind extended this idea to the entire cosmos. What if everything in our universe, every star, planet, and particle, is fundamentally encoded on a distant two-dimensional boundary, perhaps at the edge of the observable universe? In other words, our 3D reality could be a hologram. This doesn't mean the universe is fake or illusory like in the Matrix. It means that what we experience as three-dimensional space might emerge from a simpler, two-dimensional description of reality. Think of a hologram, a flat surface storing information that, when illuminated, creates the illusion of depth. Similarly, the holographic principle suggests that space, time, and gravity could emerge from information inscribed on a cosmic boundary. The principle became more than a thought experiment in 1997, when Juan Meldacena introduced the ADS/CFT correspondence, a mathematical framework showing that a universe with gravity in 3 dimensions can be equivalent to a quantum system in 2 dimensions. This offered a potential bridge between general relativity and quantum mechanics, two theories that have resisted unification for decades. If true, the implications are staggering. Space and time might not be fundamental. They could be emergent properties, like the shimmering surface of a pond hiding deeper layers beneath. The universe as we know it might not be the ultimate reality, but a projection of information encoded on a faraway surface. Experiments, such as those at Fermilab, are now probing for evidence. Tiny fluctuations in space-time, like the pixels of our cosmic screen. Whether or not proof emerges soon, the holographic principle has already transformed physics. It challenges our assumptions about dimensions, information, and the very nature of existence. So the next time you gaze up at the night sky, filled with stars scattered across infinite darkness, remember, it's possible that everything, the cosmos, space, time, even us, might just be the shadow of something deeper, written on the edge of reality itself. The universe, as we see it, shouldn't exist, not with galaxies spiraling through space, stars burning brightly, planets orbiting in silence, and certainly not with you here reading this. According to the fundamental laws of physics, every particle of matter, protons, neutrons, electrons, should have been perfectly matched by an antimatter twin, a proton by an antiproton, an electron by a positron. And when matter meets antimatter, they annihilate in a burst of pure energy, leaving only light behind. If the universe had obeyed this symmetry perfectly, nothing would remain. No stars, no planets, no life, just a cold, empty void, a faint afterglow of mutual destruction. But something broke the balance. Somehow matter won. For every billion pairs of particles and antiparticles created in the first moments of the universe, one extra particle of matter survived. That tiny 1 in a billion excess is everything. The galaxies, the stars, the swirling nebulae, and the atoms in your body. The question is, why? What happened in those first fractions of a second after the Big Bang that tilted the scales toward matter? To find the answer, we return to the chaotic, superheated infancy of the cosmos. In those first instances, energy and matter constantly transformed into each other, and symmetry ruled. But as the universe expanded and cooled, something extraordinary occurred. Symmetry broke. This fragile imbalance is the secret of our existence. In the 1960s, Soviet physicist Andrei Sakharov outlined 3 conditions necessary to create this asymmetry. Matter and antimatter must behave differently. A violation of CP symmetry, the combined symmetry of charge and parity. The universe must have been out of equilibrium, a turbulent state where interactions weren't perfectly balanced. There must have been processes that produced more matter than antimatter. It sounded straightforward, but proving it was another matter. In 1964, physicists James Cronin and Val Fitch discovered a small but undeniable CP violation in rare decays of particles called kaons. It was the first evidence that nature might favor matter over antimatter. But the effect was tiny, far too small to account for the universe's existence. Like finding a faint scratch on a massive wall, it hinted at something larger but didn't explain it. In recent years, attention has shifted to one of the most mysterious particles in physics, the neutrino. These ghost-like particles barely interact with anything. Trillions pass through your body every second without notice. Some theories suggest neutrinos might hold the key. If they are Majorana particles, their own antiparticles, they could have decayed in the early universe in a way that subtly favored matter, a process called leptogenesis. This could explain the tiny imbalance that seeded everything. But neutrinos are notoriously difficult to study. Experiments buried deep underground, shielded from background noise, are searching for the faintest trace of this behavior. So far, the answers remain elusive. Whispers in the dark, patterns hidden in the noise. Another possibility is far stranger. What if antimatter isn't gone at all? What if it exists in vast regions of the cosmos? Antimatter galaxies, antimatter stars, antimatter planets, separated from us by immense voids. If matter and antimatter ever met on cosmic scales, their collisions would light up the universe in brilliant gamma-ray bursts. Yet we see no such fireworks. If antimatter exists elsewhere, it has left no clear trace. And so the mystery endures. Somewhere, in the equations of particle physics, in the fleeting decay of kaons, in the ghostly flicker of neutrinos, or in the structure of the cosmos itself, lies the answer. An answer that could explain not just why matter exists, but why we exist. It's humbling to realize that everything, the vast galaxies, the burning stars, and life on our fragile world, owes its existence to an imperfection, a tiny asymmetry in the universe's earliest moments. Was it an accident? A random fluctuation? Or is there a deeper reason? A hidden principle woven into the fabric of reality that favors something over nothing? For now, the truth remains hidden, scattered across underground detectors, particle colliders, and telescopes scanning the heavens. With every experiment, every data point, we edge closer to uncovering the secret of why the universe is filled with something instead of nothing. And when that secret is finally revealed, we may find that this small imbalance, the crack in cosmic symmetry, was not just the origin of matter, but the spark of existence itself. The universe, vast, unyielding, and unfathomable, stretches beyond our sight, an endless expanse of stars and emptiness. Its scale defies imagination, its mysteries buried deep within cosmic shadows. Yet among all the enigmas we've uncovered, one elusive signal persists, a subtle, relentless pull, as if an unseen tide were dragging entire clusters of galaxies in one unwavering direction. This phenomenon is called dark flow, and it challenges not just our grasp of gravity, but our understanding of reality itself. In the cosmic tapestry, galaxies do not sit still. They move, drawn by gravity into clusters and superclusters, flowing along the invisible scaffolding of dark matter. Most of these motions can be explained by the expansion of space, driven by dark energy. But in 2008, scientists analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, found something unexpected: a collective drift of galaxy clusters across billions of light years, all heading in the same direction, as though caught in an unseen current. This wasn't supposed to happen. According to our best cosmological models, galaxy motions on such scales should be random, shaped only by local gravitational effects and the steady stretching of the universe. Yet here was evidence of a coherent, large-scale flow towards something beyond our view, something immense, hidden beyond the edge of the observable universe. To detect this motion, astronomers relied on the Sunyaev-Zeldovich effect, a tiny distortion in the cosmic microwave background, the ancient light left over from the Big Bang, caused by hot gas inside galaxy clusters. By measuring these distortions, they could track how clusters moved against the universe's faint afterglow. The result was stunning. Clusters spanning billions of light-years were streaming in the same direction at speeds approaching 1,000 kilometers per second. This was no minor anomaly. It suggested a gravitational influence from something vast and unseen, something beyond the cosmic horizon. Theories poured in. Some scientists proposed that dark flow might be caused by a titanic structure beyond our observable universe, perhaps a supercluster of unimaginable scale, or even a remnant of a universe that existed before ours. Others speculated about extra dimensions, with gravity seeping into our cosmos from realms we cannot perceive. The boldest idea of all suggested that dark flow could be evidence of the multiverse, our universe colliding or interacting with another, hidden beyond the veil of spacetime. The implications are staggering. The cosmic horizon, the limit of what we can observe, is not a boundary of reality, only of perception. Dark flow hints that our universe might be part of something far larger, woven into a fabric of connections stretching beyond time and space. Not everyone agrees. Later observations from missions like Planck questioned the strength of the evidence, suggesting it might be a statistical artifact rather than a true cosmic current. But many remain convinced that the signal is real, and if so, it could be one of the most profound discoveries in cosmology. Because if dark flow exists, it tells us that we are not in an isolated bubble of stars drifting quietly through emptiness. We are part of a cosmic current, a motion that carries every galaxy, every star, every world, including our own, toward an unknown destination beyond the reach of light. Perhaps we will never know what lies beyond that boundary. Perhaps the source of dark flow will forever remain hidden, veiled by the limits of observation. Or perhaps one day, new instruments and new theories will let us peer beyond our horizon and catch a glimpse of what pulls us. Until then, dark flow remains a riddle, etched into the motion of galaxies, whispered in the background glow of the cosmos. It is a reminder of how much we have yet to discover, of how small we are, and of how deeply connected we remain, to each other, to the stars, and to whatever lies beyond. In the end, dark flow is not just about galaxies drifting across the void. It is about our shared journey into the unknown. It reflects the human urge to question, to explore, and to follow the faintest signals from the universe itself. And so, we drift, all of us, carried by invisible currents toward a destination we cannot see, while, beyond the edge of light, the cosmos waits in silence. Beneath the surface of reality lies a rulebook, a set of fundamental laws that govern how the universe behaves. These laws are steady, predictable, and seemingly unbreakable. Drop a ball, and it falls. Heat flows from hot to cold. A solid wall stops you in your tracks. But deep within the quantum realm, reality begins to defy those rules. Here, particles don't behave like tiny, solid objects. They flicker, blur, and sometimes perform an act so bizarre it seems impossible. They pass through barriers as if those barriers weren't even there. This is quantum tunneling, one of the strangest and most fascinating phenomena in all of physics. Imagine standing before a mountain. You could climb over it, or dig your way beneath it, but you'd never simply pass through it. In our everyday, classical world, governed by Newtonian physics, this is unthinkable. Yet in the quantum world, particles can do exactly that. Electrons, protons, even entire atoms have been observed tunneling through obstacles they shouldn't be able to cross. How is this possible? To understand tunneling, we first need to look at how particles behave at the quantum level. In our macroscopic world, objects have well-defined positions. A marble is either here or there, never both. But in the quantum realm, particles behave as both particles and waves. They aren't located at a single point, but are instead described by a wave function, a spread of probabilities representing where they might be. Picture tossing a stone into a pond. Ripples spread out in all directions. Similarly, A quantum particle's wave function extends across space. Now place a wall in the way of those ripples. In the classical world, the ripples would stop cold. But quantum mechanically, the wave function doesn't disappear entirely. It seeps through, leaving a faint probability on the other side. And sometimes, that probability becomes reality. The particle appears beyond the barrier, as if by magic. This isn't just a theoretical curiosity. It's essential to the universe itself. Quantum tunneling is what allows stars to shine. In the heart of a star, hydrogen nuclei must overcome their mutual electrical repulsion to fuse, releasing energy as light and heat. Classically, this should be nearly impossible. But tunneling allows the nuclei to slip through the barrier, enabling fusion and powering the cosmos. Here on Earth, tunneling drives groundbreaking technologies. Scanning tunneling microscopes use it to map individual atoms. Flash memory, found in your phone and computer, relies on electrons tunneling through insulating layers to store information. Yet tunneling has limits. The thicker or taller a barrier, the less likely a particle is to pass through. Its probability decays exponentially. Tunneling isn't a loophole to escape reality. It's more like rolling infinite dice and occasionally, against all odds, getting the perfect result. Scientists have even pushed tunneling to new extremes, coaxing entire molecules and clusters of atoms through barriers. But could something macroscopic, a cell, a virus, or even a human, ever tunnel through a wall? Theoretically, yes. Practically, no. The odds are so vanishingly small that they're effectively zero, less likely than randomly assembling Shakespeare's Hamlet by tossing Scrabble tiles into the air. Even at the quantum scale, mysteries remain. How long does tunneling take? Is it instantaneous? Recent experiments using ultra-fast lasers suggest tunneling might happen faster than we ever imagined, perhaps with no measurable duration at all. And some physicists wonder if tunneling could reveal something deeper, hidden dimensions, unknown physics, or even clues to a theory of everything, a framework uniting quantum mechanics, gravity, and the entire cosmos. Ultimately, quantum tunneling reminds us that reality, at its core, is not solid and predictable. It is fluid, probabilistic, and astonishingly strange. Particles ignore boundaries, appearing where they have no right to be. They blur the line between here and there, between impossible and real. So, the next time you gaze at the light of a distant star or save a photo on your phone, remember, somewhere in the fabric of existence, particles are slipping through barriers, breaking rules, and proving that the universe is far stranger and far more beautiful than we ever dared to imagine. And perhaps, hidden within the final mysteries of quantum tunneling, lies the key to the next great revolution in our understanding of reality. The question isn't if we'll break through that barrier, it's only when. Somewhere in the intricate workings of the cosmos, woven into the very dance of particles and forces, there may be something more, something beyond what we know, a fifth force of nature. For centuries, physics has been built upon four foundational forces: gravity, electromagnetism, and the strong and weak nuclear forces. Together, they govern everything, from the swirling motion of galaxies to the behavior of subatomic particles. Yet, as powerful as these four pillars are, they leave gaps, questions unanswered, phenomena unexplained. Could there be another force, hidden just beyond our reach? The search for such a force began not with modern supercolliders, but with an old puzzle: gravity. In the early 20th century, Albert Einstein revolutionized our understanding of it through general relativity, showing that gravity is not a conventional force, but the curvature of space-time itself. His theory describes the large-scale universe with stunning accuracy. But at the tiniest scales, where quantum mechanics dominates, gravity does not seem to fit. Our two greatest theories of nature, one for the vast and one for the small, cannot be reconciled. This deep incompatibility opened the door to speculation. Could something else, an unknown interaction, be hiding in the gap between the cosmic and the quantum? In 2015, at the Atomiki Institute in Hungary, a team led by Attila Krasznahorki stumbled upon a curious anomaly while studying the decay of an excited beryllium-8 nucleus. Their data revealed a small but unexplained excess, a potential sign of a new particle. They called it the X-17 particle, a hypothetical boson with a mass of around 17 megaelectron volts. If real, X-17 could be the messenger of an entirely new force of nature. Skepticism was immediate. Extraordinary claims demand extraordinary evidence. Still, the possibility was electrifying. What kind of force might X-17 represent? Some theorists suggest it could be a dark force, one that interacts primarily with dark matter, the invisible substance making up most of the universe's mass. If so, this fifth force could help explain long-standing mysteries, the strange rotation of galaxies, oddities in gravitational lensing, even the accelerating expansion of the universe. The implications would be staggering. A fifth force might unify fragmented pieces of modern physics, bridging the gap between quantum mechanics and gravity. It could reshape our understanding of reality itself. But for now, the evidence remains tentative. Other experiments, including high-energy collisions at the Large Hadron Collider and ultra-precise atomic clock measurements, are searching for confirmation, but so far, no definitive proof has emerged. Science, however, thrives at the boundary of the unknown. Many of physics' greatest breakthroughs, the curvature of space-time, quantum uncertainty, the dual nature of light, began as faint anomalies, puzzling signals whispering of something greater. If a fifth force exists, its discovery would not just expand our scientific framework, it would remind us of something profound. The universe still holds secrets in plain sight, waiting for us to notice. For now, the fifth force remains a tantalizing question, a mystery suspended between theory and evidence. Perhaps tomorrow, perhaps decades or centuries from now, we will finally uncover it. One thing, however, is certain: the cosmos has not finished surprising us, and likely never will.